And now in this lecture we'll find out the radius of a circle using two different methods. In the drawing we have triangle ABC. Triangle ABC blocks this circle, or this circle is inscribed by triangle ABC. In addition, we know that angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle. We will start with the first method, and we will do a construction. That is to say, from point C, we will draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB as D. So actually, by doing this construction, we created here triangle BDC. So I'll copy this triangle BDC in a new page, and we will analyze this triangle BDC. So actually, this is triangle BDC that I copied from the original drawing. BC equals to 2 and angle DBC equals to 60 degrees according to what is given as the question. So in this right triangle DBC, cosine 60 degrees equals to DB over BC. So it is DB over BC, and BC is 2, so we substitute BC by 2. So cosine 60 degrees is 1/2, so we substitute cosine 60 degrees by 1/2, so 1/2 equals to DB over 2. Here we will multiply this equation by 2, and finally we will get that side dB, 97 dB, equals to 1 unit in its length. dB equals to 1 unit in its length. You can write here that this 97 dB equals to 1 unit in its length. We continue to focus on this right triangle DBC. On the right triangle DBC, sinus 60 degrees equals to DC over BC. Okay, so sinus 60 degrees is equal to 3 over 2. That is equals to DC over BC, and BC is 2, so we substitute BC by 2. In conclusion, found out that square root of 3 over 2 equals to DC over 2. Here we will multiply this equation by 2, and finally we get that DC equals to the square root of 3 units in its length. Okay. Here DC equals to the square root of 3 units in its length. So in the same right triangle DBC, the sum of the angles must be equal to 180 degrees, the rule that is true in any triangle. So which angles we have in the right triangle DBC? This is a right angle that is equal to 90 degrees, plus this angle that is 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle here must be equal to 30 degrees in its size. In order to complete the sum of the angles in this triangle DBC to 180 degrees, the missing angle here must be equal to 30 degrees. Okay, it is given as the question that the big angle ACB equals to 75 degrees in its size. This is the big angle ACB minus the small angle, that's the actual angle DCB. The big angle minus the small angle will be equal to this missing angle. Again, the missing angle here must be equal to the big angle minus the small angle. The big angle equals to 75 degrees, the small angle equals to 30 degrees, so 75 degrees minus 30 degrees equals to 45 degrees. So the missing angle DCA equals to 45 degrees in its size. In the next step, I will copy the right triangle DCA in a new page and we will analyze this right triangle DCA. So actually, this is the right triangle DCA that I copied from the original drawing. This is the missing angle that we found, that's equal to 45 degrees in its size. And we have already found out that this equals to the square root of 3 units. So in this right triangle, the sum of the angles must be equal to 180 degrees. So which angles we have in this right triangle DCA? This angle equals to 90 degrees, plus this angle that is 45 degrees. 90 degrees plus 45 degrees, it is equals to 135 degrees. Therefore, the missing angle here must be equal to 45 degrees. In order to complete the sum of the angles in this right triangle DCA to 180 degrees, the missing angle here must be equal to 45 degrees. So, in the right triangle DCA, those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle, they are equal sides. So those two sides that are located in front of those two equal angles must be equal to each other. That is to say, side AD must be equal to side DC, according to the rule that I mentioned. But DC equals to the square root of 3 units. So I can write down here that DC equals to the square root of 3. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that AD also equals to the square root of 3 units in its length. If this side AD equals to the square root of 3 units in its length, you can write here that this line segment AD equals to the square root of 3 units in its length. We will continue to focus on this right triangle ADC. We will implement on this right triangle ADC the Pythagoras theorem. by PT is the provision for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ABC, the square of the hypotenuse equals to the sums of the squares of the perpendiculars. That is to say, the hypotenuse is AC, so the square of the hypotenuse is AC squared, and it must be equal to AD squared plus DC squared. AC squared, that is the square of the hypotenuse, equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is square root of 3 squared, that is also 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We take a root out of this equation, and finally we get that AC equals to the square root of 6 units. Here, the side AC of this triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to, the radius R equals to the area of triangle ABC over S. S is the semi-perimeter of the same triangle ABC. And the semi-perimeter of any triangle is the perimeter over 2. So the drawing of this rule, rule number 15, this is the drawing. So in the drawing we have a circle that is inscribed by triangle ABC. So the radius of this circle R will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is inscribed by triangle ABC. So whenever we have a circle that is inscribed by triangle, we can implement rule number 15. Okay, so according to all, we define the radius of this circle as R. So the radius R, according to rule number 15, the radius R of this circle will be equal to the area of triangle ABC that blocks this circle over the semi-perimeter of the same triangle ABC. So this equation is the implementation of rule number 15 in our drawing. The radius R of our circle, the radius R of this circle, according to number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So the area of triangle ABC divided by S, that is the semi-perimeter of the same triangle ABC. So we choose the base of this triangle ABC as AB, and the height to the base will be CD, because CD creates 90 degrees with the base AB. Again, the base is AB, and the height to the base is CD, divided by 2, all divided by S, that is the semi-perimeter of the same triangle ABC. AB equals to the square root of 3 plus 1 times CD. CD equals to the square root of 3, all divided by 2, and we have to divide it by S, that is the semi-perimeter of the same triangle ABC. The semi-perimeter of this triangle ABC equals to the perimeter over 2. The perimeter of this triangle ABC is the sum of its side lengths, that is to say it is AB plus BC plus AC. If we divide it by 2, we get the semi-perimeter S of our triangle ABC. So this expression is the area of triangle ABC. That is actually square root of 3 plus 1 times square root of 3 over 2, and we have to divide it by the semi-perimeter, and the semi-perimeter is AB, that is square root of 3 plus 1 plus BC. BC equals to 2 units according to what is given as the equation, but plus AC. We have only found out that AC equals to the square root of 6 units in its length, that is plus square root of 6 units, all divided by 2. So this expression in total is the semi-perimeter of triangle ABC, and this expression in total, it is the area of triangle ABC. The value of this expression, that is the area of triangle ABC, is actually equals to 2.366 square units divided by the semi-perimeter of the same triangle ABC. The semi-perimeter is the value of this expression, and the value of this expression is actually equals to 3.591, and 2.366 over 3.591 is equals to 0.6589. So in conclusion, we found out that the radius R of this circle equals to 0.6589 units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the radius of this circle according to the second method. We define the center of this circle as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And finally, we define the point of tendency of tangent BC with this circle as D. We will join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We will define the radius of this circle as R, so OD equals to R. We can implement here rule number 1. What is rule number 1? According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have here tangent AB, that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. We can actually implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius OD that is drawn to point D. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If this is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Likewise, we join points O and D together by a straight line. OE is the radius of this circle that is equals to R. Again, we have here the radius OE that is drawn to point E, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle also equals to 90 degrees. We join points O and F together by a straight line. OF is the radius of this circle that is equal to R. Again, the radius OF is drawn to point F. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. You can implement also here rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and a common external point, point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. Okay. We can actually implement rule number 2 in our drawing. I repeat again, we can implement rule number 2 in our drawing. We'll focus on at the common external point, point C. Here, from the common external point, point C, we have two tangents to this circle, tangent CF and tangent CD. According to rule number 2, they are equal to each other. That is to say, CF equals to CD. So I write it down. CF equals to CD according to rule number 2. Likewise, we will focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle. Tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. So I write it down. BE equals to BD according to the same rule, rule number 2. In the next step, we will join points O and C together by a straight line. And we will join points O and B together by a straight line. We prove that those two right angles can go into each other. That is to say, we prove that the green right angle triangle BOD is congruent to the yellow right triangle triangle EBO. So write it down. We prove that the green right triangle triangle BOD is congruent to the yellow right triangle triangle EOB. So why those two right angles can go into each other? First of all, side EO of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. So I write it down. Repeat again. Side EO of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. Here, BE equals to BD according to rule number 2. Repeat again. Side BE of the yellow triangle equals to side BD of the green triangle according to rule number 2. And finally, we have side OB is the common side that belongs to both triangles, so we can write down that side OB equals to itself as a common side that belongs to both triangles. OB equals to itself. Repeat again. Side OB equals to itself as a common side that belongs to both triangles. So I shall prove that all the three sides of the yellow right triangle EOB are correspondingly equal to all the three sides of the green right triangle OBD. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The green triangle BOD is congruent this is the sign of congruent to the yellow triangle EOB, according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So this is angle EBO in the yellow triangle. And it is equal to this angle, this is actually angle OBD in the green triangle. So we derive that angle EBO equals to angle OBD. So if we define one of those angles as theta, then the other angle must be also equal to theta because they are equal to each other. So if this angle is theta, then the other angle must be also equal to theta. So theta plus theta in total must be equal to 60 degrees. So can I write down that 2 theta equals to 60 degrees. We divide this equation by 2. And finally we get that angle theta equals to 30 degrees in its size. So actually this is angle theta that is equal to 30 degrees in its size. In the next step I'll copy the green right triangle OBD in the new page and we will analyze this right triangle OBD. So actually this is the green right triangle OBD that I copied from the original drawing. Angle OBD equals to theta, that is 30 degrees, and side OD equals to R, that is the radius of the circle. So in this right triangle OBD, tangents 30 degrees equals to OD over BD. So tangent 30 degrees equals to OD. OD is R, so it is R over BD. In conclusion, found out that tangents 30 degrees equals to R over BD. Here we multiply this equation by BD and we get that BD times tangents 30 degrees equals to R. Here we'll divide this equation by tangents 30 degrees and finally we get that BD equals to R over tangents 30 degrees. So this line segment BD equals to R over tangents 30 degrees in its length. So I write it down. BD equals to R over tangents 30 degrees In the next step, we repeat on the same process on those two right angles. We'll actually prove that those two right angles can go into each other according to side rule. So we'll actually prove that the orange triangle ODC actually it is the pink triangle ODC is congruent to the orange triangle OFC. Okay. Repeat again, we prove that the pink triangle ODC is congruent to the orange triangle OFC. So I'll do it quickly because we already done it in those two right angles. So here side OD equals to side OF. They are both the radii of the circle, therefore they are equal to each other. OD equals to OF. In addition, CD equals to CF according to rule number 2. Here, CD equals to CF according to rule number 2. And finally, side OC is a common side that belongs to both triangles, so we can write down that OC equals to itself as a common side that belongs to both triangles. So we're going to prove that all the three sides of the pink triangle ODC are correspondingly equal to all the three sides of the orange triangle OFC. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The pink triangle ODC is congruent to the orange triangle OFC. According to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent angles are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha, in total, they are equal to 75 degrees. 2 alpha equals to 75 degrees. We divide this equation by 2. And finally, we will get that angle alpha equals to 75 degrees over 2, that is 37.5 degrees. So actually, this is angle alpha, that is equals to 37.5 degrees in its size. The next step, I'll copy the pink triangle ODC in a new page and we'll analyze this pink triangle, triangle ODC. So actually, this is the pink triangle ODC that I copied from the original drawing. In this pink triangle ODC, tangents 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So in conclusion, found out that tangents 37.5 degrees equals to R over DC. So here we will multiply this equation by DC and we get that DC times tangents 37.5 degrees equals to R. Here we will divide this equation by tangents 37.5 degrees. And finally, we get that DC equals to R over tangents 37.5 degrees. Okay. So actually, this line segment DC equals to R over tangents 37.5 degrees. So I write it down. From the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. So I write it down. BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC is 2, according to what is given in the question, so we'll substitute BC by 2. And it is equals to BD. BD equals to R over tangents 30 degrees, so we'll substitute BD by R over tangents 30 degrees. plus DC. We already found out that DC equals to R over tan 37.5 degrees. So if we're going to find out that 2 equals to R over tan 30 degrees plus R over tan 37.5 degrees. So 2 equals, here we take out R as a common factor from those two expressions. So R was taken as a common factor. What is left from this expression after we took omit R as a common factor? What is left? It is actually 1 over tan 30 degrees plus what is left from this expression after we took R as a common factor, after we took from it R as a common factor, what is left? It is actually 1 over tan 37.5 degrees. So we found out that 2 equals to R times 1 over tan 30 degrees equals to 1.732 plus 1 over tan 37.5 degrees. 1 over tan 37.5 degrees equals to 1.3032. So we can find out that 2 equals to R and 1.732 plus 1.3032 equals to 3.0352. So we can find out that 2 equals to R times 3.0352. Here we divide this equation by 3.0352, and finally we get that R, the radius that we are looking for, the radius of the circle R, equals to 2 over 3.0352. 2 over 3.0352 equals to 0.6589 units. You can find out that R equals to 0.6589 units. So in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, we finished with the second method. In the next step I will summarize the lecture. We'll start with the first method. In this lecture we found out the radius of this circle. In the drawing we have a circle that is inscribed by this triangle ABC. In addition we know that this angle ABC equals to 60 degrees in its side, and this is angle ACB that is equals to 75 degrees, and side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle. In the first method we did a construction, that is to say, from point C we draw perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. By doing this construction we created here the right angle DBC. So I copy the right angle DBC in a new page and we analyze this right angle triangle DBC. This is the right angle DBC that I copied from the original drawing. Angle DBC equals to 60 degrees and BC equals to 2 according to what is given in the question. In this right angle DBC, cosine 60 degrees equals to DB over BC. DB over BC. So DB over BC, and BC is 2, so it is DB over 2. Cosine 60 degrees is 1/2, so we found out that 1/2 equals to DB over 2. Here we multiply this equation by 2, and finally found out that BD equals to 1 unit in its length. Here, this line segment BD equals to 1 unit in its length. We continue to focus on the right triangle, triangle DBC. On the right triangle, triangle DBC, sine of 60 degrees equals to DC, sine of 60 degrees equals to DC over BC. Sine of 60 degrees equals to DC over BC. So it is, and sine of 60 degrees is equal to 3 over 2. That is equals to DC over BC, and BC is 2. So we found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2. And finally found out that DC equals to the square root of 3 units in its length. This line segment DC equals to the square root of 3 units in its length. Here, this line segment DC equals to the square root of 3 units in its length. So we continue to focus on the right triangle DBC. On the right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle DBC? This angle equals to 90 degrees, this angle equals to 60 degrees, 90 degrees plus 60 degrees, it is 150 degrees. Therefore the missing angle here must be equal to 30 degrees in its size. Okay, so the big angle ACB, this is the big angle that is equal to 75 degrees in its size according to what is given as the question. We just right now found out that the small angle DCB equals to 30 degrees. So the big angle ACB minus the small angle DCB must be equal to the missing angle, this missing angle, angle ACD. Therefore, the missing angle ACD equals to the big angle that is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees, it is 45 degrees. So angle ACD equals to 45 degrees in its size. Then I copy the right triangle ACD in the new page and we analyze this right triangle, triangle ACD. This is right triangle, triangle ACD that I copied from the original drawing. The sum of the angles in this right triangle, triangle ACD must be equal to 180 degrees. So which angles we have in the right triangle ACD? We just right now found that this angle equals to 45 degrees, this angle equals to 90 degrees, 90 degrees plus 45 degrees equals to 135 degrees, therefore the missing angle here must be equal to 45 degrees. In order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees. So those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle they are equal sides. That is to say, side AD must be equal to side DC because those two sides are located in front of those two equal angles, therefore they are equal to each other. AD equals to DC. But we have already found out that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that side AD also equals to the square root of 3 units in its length. If the side AD also equals to the square root of 3 units in its length, so we can write down in the original drawing that this side AD equals to the square root of 3 units in its length. We continue to focus on the same right triangle, triangle ADC. We implemented the Pythagoras theorem in this right triangle, triangle ADC. According to the Pythagoras theorem in this right triangle ADC, AC square equals to AD square plus DC square. Again, AC square equals to AD square plus DC square. AC square, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is also equal to 3, therefore DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. So AC squared equals to 6. We took a root out of this equation, and finally found out that AC, the important AC equals to the square root of 6 units in its length. Here, side AC of this triangle ABC equals to the square root of 6 units in its length. Then I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to the radius R equals to the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle ABC. The drawing of this rule is here. We have a circle that is inscribed by triangle ABC. So the radius of this circle that is inscribed by triangle ABC, the radius R will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is inscribed by a triangle. Whenever we have a circle that is inscribed by a triangle, we can implement rule number 15. So the radius, we define the radius of this circle R. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. I'll repeat again. According to rule number 15, the radius R of our circle, the radius that we are looking for, equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The area of any triangle is the base of the triangle times the height of the base over 2, divided by S, that is the semi-perimeter of the same triangle ABC. We choose the base of this triangle ABC as AB, and the height to the base is CD. Because CD creates 90 degrees with the base AB. Again, the base is AB and the height is DC divided by 2. All divided by S, that is the semi-perimeter of the same triangle ABC. AB is equal to 3 plus 1, DC is equal to 3 divided by 2. So in total, this expression equals to the area of triangle ABC divided by S, that is the semi-perimeter of the same triangle ABC. The semi-perimeter of our triangle ABC equals to the perimeter, that is AB plus BC plus AC divided by 2. AB is equal to 3 plus 1, BC is 2, and AC is equal to 6, all divided by 2. So this expression is the area of triangle ABC. The value of this expression is 2.366 over this expression. This expression is the semi-perimeter of triangle ABC, and the value of this expression in total it is equals to 3.591. And 2.366 over 3.591 is equals to 0.6589. In conclusion, found out that the radius R of this circle equals to 0.6589 units. We finished with the first method. Then I presented to you how to find out the radius of this circle according to the second method. In the second method, we define the center of this circle as O. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent BC with this circle as D. Then we join points O and D together by set line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, therefore OD equals to R. We have the radius of OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. That whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We join points O and D together by set line. OE is the radius of this circle that is equal to R. The radius OE is drawn to point E, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, we join points O and F together by set line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, that is the point of tendency of tangent AC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, then this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Then I presented to you rule number 2. We actually focused on the common extreme point C. For the common extreme point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say here, CF equals to CD according to rule number 2. Likewise, we focused on the common extreme point B. From the common extreme point B, we have two tangents to this circle, tangent BD and tangent BA. According to rule number 2, they are equal to each other. That is to say, BE equals to BD. Then we join points O and C together by side line, and join points O and B together by side line. Then we proved that the yellow triangle is congruent to the green triangle according to side rule. Why those two right triangles congruent to each other? First of all, EO equals to OD. They are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. BE equals to BD according to rule number 2. And finally, side OB is a common side that belongs to both triangles. So side OB equals to itself is a common side that belongs to both triangles. So actually proved that all the three angles of the yellow right triangle EOB are corresponding equal to all the three sides of the yellow right triangle EOB are corresponding equal to all the three sides of the green right triangle ODB. Therefore, we proved that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees according to what is given as the question. So 2 theta equals to 60 degrees. Here, 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that angle theta equals to 30 degrees in its size. So this is angle theta that equals to 30 degrees in its size. Then I copied the right triangle OBD in a new page and analyze this right green triangle OBD. This is the right green triangle OBD that I copied from the original drawing. From the drawing, it is very easy to see that tan 30 degrees equals to OD over BD. Tan 30 degrees equals to OD over BD. OD is R, so it is R over BD. So tan 30 degrees equals to R over BD. Here we multiply this equation by BD and finally found out that R times tan 30 degrees, tan 30 degrees times BD equals to R. BD times 30 degrees equals to R. Here we divided this equation by tan 30 degrees and finally found out that BD equals to R over tan 30 degrees. Here this line segment BD equals to R over tan 30 degrees in its length. Then we proved that those two right triangles can go into each other according to side rule. Why those two right triangles can go into each other? First of all, OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. Again, here, CF equals to CD according to rule number 2. And finally, side CO is a common side that belongs to both triangles, so we can write down that CO equals to itself as a common side that belongs to both triangles. So actually, prove that all the three sides of the orange right triangle FCO corresponding equal to all the three sides of the pink right triangle OCD. Therefore, we actually proved that those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. So if this angle equals to alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees according to what is given as the question. So 2 alpha equals to 75 degrees. Here 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 75 degrees over 2, that is 37.5 degrees. So here, okay, this is angle alpha that is equal to 37.5 degrees. Then I copied the pink right triangle ODC in the new page and we analyze this pink right triangle ODC. This is the pink right triangle ODC that I copied from the original drawing. In this right triangle ODC, triangle 37.5 degrees equals to OD over DC. Okay? OD is R, so times 37.5 degrees equals to R over DC. Here we multiplied this equation, here times 37.5 degrees equals to R over DC. We multiplied this equation by DC and finally found out that R equals to DC times 37.5 degrees. Here we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Here, this line segment DC equals to R over times 37.5 degrees. From the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC is 2, BD is R over tangent 30 degrees, and DC is R over tangent 37.5 degrees. So in conclusion, found out that 2 equals to R over tangent 30 degrees plus R over tangent 37.5 degrees. Here we took out R as a common factor from those two expressions and found out that 2 equals to R. R was taken out as a common factor. So what is left from this expression after we took R from it as a common factor? What is left is R over tangent 30 degrees. And what is left from this expression after we took from it R as a common factor? What is left is actually R over tangent 37.5 degrees. So in conclusion, we found out that 2 equals to R times 1 over tangent 30 degrees plus 1 over tangent 37.5 degrees. All those two expressions in brackets. Okay. So 2 equals to R and 1 over tangent 30 degrees is 1.732 plus 1 over tangent 37.5 degrees is 1.0332. Again, 1 over tangent 37.5 degrees is 1.3032. So in conclusion, found out that 2 equals to R times 1.732 plus 1.3032. 1.732 plus 1.3032 equals to 3.0352. So in conclusion, found out that 2 equals to R times 1.30352. We divided this equation by 3.0352 and finally found out that R, the radius of the circle that we are looking for, equals to 2 over 3.0352. That is actually 0.6589 units. So actually in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.